Hello, everyone, and welcome to our second review session for AP Physics 1. In our first session, which we had last week, we talked a little bit about the test structure, what that would look like. We also talked a little bit about some general test strategies and techniques to help improve our scores, perhaps outside of the content. And then we started in on the content a little bit. We touched on some definitions in kinematics, which is Unit 1, talking about things like distance and displacement, speed and velocity and acceleration. And what we're going to do now going forward is focus on the content. So in today's session, we're going to keep talking about kinematics. In particular, we'll build on what we did last time by bringing up a special kind of motion that's commonly tested on AP Physics 1, which is uniformly accelerated motion. From there, we'll discuss where accelerations come from and how motions can change, getting into a conversation on Newton's laws and forces. So that takes us through the dynamics unit. And then we'll look at circular motion, a special kind of motion that we'll be able to talk about now that we would have covered terms from kinematics as well as Newton's laws. And in that conversation, gravitation is a common example of a force that can lead to circular motion. So we'll also touch on gravitation. Based on time, we might be able to say the odd thing from the energy unit, maybe not. But we do have a third review session on April 22nd, same time as now, 6 p.m. Eastern time. And in that session, we'll take up the rest of the content. So we'll get into topics on energy, momentum, simple harmonic motion, torque, and rotation. So if we're interested in catching all that, do tune in on April 22nd at 6 p.m. Eastern. But for today, we're going to get into what we see listed here, and that starts with kinematics. So let's take a look at that. So last time, like I said, we got into some of the definitions. We learned about some of the common terms when it comes to describing motion. But now what we're going to focus on is this uniform accelerated motion, which is to say movement where the acceleration is uniform or constant is what that really means. So if you can spot in a question that the acceleration is constant, then you're in a position to perhaps be able to use what we call the big five, shown right here. And while I know that might not be the most exciting thing to see 5 equations on our board, I will tell you that there are a number of things that are actually pretty nice about having the 5 equations and pretty redeeming about the setup here. First off, 3 of these equations I'd anticipate would be given to you on your exam equation sheet, particularly big fives number 2, 3, and 5. So that's nice. Uh, but what's also nice are the variables that are involved in the equations. And we list them off here, where this delta x is your displacement, v naught is the initial velocity, v is the final velocity, a is the acceleration, and delta t is the time. So that gives us 5 unknowns for the 5 equations listed. And whenever you've got the same number of unknowns as you do equations, you're in a mathematically happy place, right? It means we should have some confidence that there's a solution there to be found, which is always nice to know. But more than that, you don't have to worry on this test about juggling 5 equations at the same time. Instead, it's going to be our goal as a test taker to figure out, well, which one of these equations do I need for my question? And that's also not too bad to figure out because of how these equations happen to be written. And they so happen to be written in a way that has them missing uniquely one of those 5 variables. And we have that listed over here. So we can see big 5-1 is missing acceleration. Big 5-2 is missing the displacement. Big 5-3 is missing final velocity. Big 5-4 initial velocity, and big 5-5 time. So that's quite useful because it gives us an approach to get into these problems. So what you want to do is ask yourself, first off, what do I want? What did they ask me for? And then take a look through the question and say, well, what did they give me to help find that quantity? And when you think about that list of what you want and what you're given, you should find that there are 4 of those variables listed. And it's that 5th one that's missing from your list that tells you which equation to work with. So grab the right equation, set it up, and solve. So instead of me just telling you that, why don't I show you now? So with this example, it says an object with an initial velocity of 4 meters per second moves along a straight axis under constant acceleration. So there you go. There's that reference that, hey, the big 5 could help out here. It says 3 seconds later, its velocity is 14 meters per second. And the question asks, how far did it travel during that time? Well, knowing that we can go down this road of using the big 5, let's start by making that list, right? what do we want? Well, it asked how far. So that's something we can infer from the displacement. And what are we given in the question to help? Well, there was that initial velocity of 4 meters per second, a later velocity of 14 meters per second, and there was a time frame of 3 seconds. And so when you look at that list, we've got displacement, we've got both of the velocities, time is there. What's missing is that acceleration. I know it's constant, but I have no idea what numerical value it has. So if the acceleration is missing, we need to use the big five that doesn't have the acceleration, and that would be big five number 1. So let's set that up. You can jot down the equation. And this is a number crunching question, right? There's a numerical value for us to find. And when we're in that position, I'm a big advocate for rearranging for what you're looking for first before you plug in numbers. And I say that for a few reasons. For one thing, some of your questions are algebraic, right? Start with some foundational principle or equation and then rearrange and solve. So we might as well do that anyway here. It's good practice. Uh, but also, the earlier you put in the numbers, the more math you're going to end up having to do, like the more number crunching, which introduces more opportunities to potentially get the math wrong, and we want to avoid that. Also, we might find through rearranging the equation some terms whose numbers maybe we won't need because maybe they drop out somehow. So rearrange for what you want first. Of course, here there's no need to do that because what we want is already isolated on the left. So here we can just plug in. So the initial velocity was 4, final velocity is 14, time involved is 3 seconds. Simplifying this, I'd put together the numbers in the parentheses to get 18. And then just wanting to do this with mental math, even though there's a calculator available, instead of going to bigger numbers first, right, 18 onto 3, which I know a lot of students are tempted to do first, realize you can multiply these in whatever order you want. And I think for mental math, going smaller is better. So let's do 1/2 onto 18 first, because that's just going to become 9. And then 9 times 3 will get us 27. And notice the units, right? Everything we've been using here, meters per second, seconds, all SI units. So the displacement we're finding would have units of meters. So there you go, right? Classic kind of uniform accelerated motion problem. A variation on this problem that we can turn our attention to next is to look at projectile motion. So still uniform accelerated motion, but now instead of having the object moving, like on a straight axis, like it says here, or just moving in the one direction, now we can have a scenario where you've got something projected. So it goes up and down while also left and right, like firing a cannonball, throwing a football, something like that. And that's what we're trying to show in the figure that we have right here. So the object will be launched at a certain angle from the horizontal, and that causes it to sort of trace out this parabolic trajectory. But notice the motion is up and down and also left and right. So 2 dimensions. And when it comes to having these vectors, right, displacements, velocities, accelerations, in 2 dimensions, we're going to break up our vectors into components. And with projectile motion, like we have here, we're going to use standard axes, coordinate axes, x, y, right, horizontal and vertical, to work our problems. And for these kinds of questions where something is launched or thrown and you've got this projectile motion, um, the object in question is going to feel just the one force. Can anyone tell me what one force will our object feel, whether it's that cannonball or that football that's flown through the air? You can just give an answer in the YouTube chat, and Shadna will relay that to me. What force will our object feel as it goes through the air? Any guesses? Okay, there we go. Good. Yeah, gravity, right? Perfect. Thanks. Yeah, so it feels that gravitational pull. And the sort of neat thing about gravity is that it's always acting downward, downward. There we go. So constant direction. And it has that fixed magnitude, which we usually label with little g, which has a value of 10 meters per second squared. Um, you don't have to quibble on the AP Physics 1 test as to whether, well, should we use 9.8 instead of 10 or 9.81, right? I think even on the test, they'll tell you it doesn't matter. I think on that equation sheet. Um, yeah, so on their equation sheet, you can imagine they might say 9.8, but in some problems they'll even say you can use 10. If you look at the grading rubrics for past tests, you'll see they'll give credit for using 10 meters per second squared. So we end up having this magnitude for little g. And if it's always downward as a direction, but we're going to take up to be positive, then the acceleration will be negative of g, right? But long story short, you have a constant acceleration, one direction, one magnitude. And what that means is you've got uniform accelerated motion, so the big five apply. But now that we've got our vectors in 2D, we're going to break up the big five. So we'll have the big five for the horizontal direction, and then we'll have the big five for the vertical direction and the components there, which at first glance kind of sounds like, well, are we now dealing with a big 10, right? Which seems a little bit unappealing. But the big five in these different directions simplify actually greatly when we consider the acceleration constraints. So if our acceleration here is all in the vertical direction, right? Negative g, negative 10 meters per squared, well, then that means there's no acceleration in the horizontal direction. And if there's no acceleration in the horizontal direction, well, then there's no change in the velocity. So that simplifies a number of the big five for the horizontal components. For the vertical components, we have big five number 2 listed here, right? But in terms of those components again, so V final in the vertical is V initial in the vertical plus acceleration times time. But of course, the acceleration in the vertical is negative g. You can also write out something similar for big five number 5. So V final in the vertical squared is V initial in the vertical squared plus twice the acceleration, which again is negative g, times that vertical displacement. And then speaking of displacements, we have a couple of equations for the displacements that pop out of, again, our big five when you look at components. So in the horizontal direction, if the velocity is constant, if that component in the horizontal is constant, then the horizontal displacement is that speed times time, that horizontal speed times time. And then for the vertical motion, we basically have big five number 3. And so when it comes to dealing with projectiles, we actually don't have quite as much as we thought we would have at first, right? Which is nice. And I'll tell you, for a lot of questions when it comes to dealing with projectiles, you'll often be dealing with one of the displacement equations or maybe both simultaneously. And if you would like to look at a number of example problems that show the different ways this could be tested and how we might use these different equations, I can recommend the Princeton Reviews AP Physics 1 prep text. Check that out. But in any case, what we want to do now is get into an example. So taking a look at this question, it says, an object is thrown horizontally with an initial speed of 10 meters per second. It hits the ground 4 seconds later. And the question asks, how far did it drop in 4 seconds? So does anyone want to tell me what language is in the question that suggests we've got free fall, suggests that the only kind of force that's present is gravity? What wording or language gives that away for us? You can just throw those guesses in the chat box, and Shadna will bring that over to me. Let me know if you need me to drop any hints for you folks. That's right, drop. Yeah, that's one case, right? If an object is dropped, it's going to fall, and it'll fall under the influence of gravity alone. If we throw the object here, it'll be, somehow projected and thus moving under the influence as a projectile under the influence of gravity, right? So there's some clues there to let us know, hey, we've got um, uniform acceleration, so the big five apply. The fact that we've thrown it now suggests, okay, we've got projectiles, and we'll have to think about the big five in terms of components. But what can really help us visualize what's happening here and give context to some of these numbers is just a quick sketch at the problem. So there's a certain height from which an object is thrown. We're told that it's thrown horizontally, so this initial velocity is horizontal with this speed of 10 meters per second. And can anyone tell me if the object is thrown horizontally, what's the magnitude of the initial vertical velocity? If our object is thrown horizontally like this, then initially, what is the vertical velocity? And I ask not just as a neat kind of idea or concept to tease out, but I ask because it becomes something we'll need to actually answer the question. And it's a zero. That's exactly it. Good job. So if all the motion is horizontal, then initially there is no motion in the vertical, right? So we get 0 meters per second for that initial vertical velocity. So the question is asking how far the object dropped, which means we need to find displacement, that vertical displacement. And so we can write out our vertical displacement equation. And like I said, we need that vertical velocity, right? Because it's embedded in that equation. So notice before I said, wait to plug in numbers. And I agree, we should wait to plug in numbers, but an exception to that is a zero, because that tends to just simplify what we're working with. So for instance, here, now that we know that the initial vertical velocity is zero, we can have this middle term vanish on us, which means what we're left having to play around with is delta y is equal to minus 1/2 gt squared. And here we can plug in numbers. So little g is at 10 meters per second squared. T was 4 seconds in our problem, and we're going to square that. So 4 squared is 16, times 10 is 160, cut in half is 80, and we've got that minus sign. And so notice what this is telling us, right? Delta y is negative 80 meters. Remember, this is your displacement vector. And we've been using those usual coordinates of to the right and up as being positive. So what this quantity tells us is the object moved in the negative direction or downward overall, a total amount of 80 meters. So it started here and vertically it finished 80 meters below that. So if the question is really asking in terms of like how far did it drop, maybe it's asking for the height of this cliff or whatever this problem has. The answer choices would all be positive quantities reflecting that height. But there wouldn't be any ambiguity in the answer choices in terms of, well, is it plus or minus 80, right? You wouldn't have to worry about that. But if the question asks for the object's displacement, well, then that's that 80 meters downward. If they wanted the height or that length that it dropped through, then that would be the 80 meters here. Okay, so that's our look at projectile motion, and that rounds out what I wanted to cover here for some kinematics review. I should say, if we have questions at any point that we're progressing along, do chime in, right? Even if I have to flip back to something I moved on from, don't hesitate to ask. But what I do want to move on to next is our conversation on dynamics. And like I said, this is really us addressing where these constant accelerations are coming from, how motions can change, and that all centers around Newton's laws. Right. So one day, once upon a time, Newton was just sitting around bored and he said, let's figure out how the universe works. So he went ahead and did that. Right. No big deal. And his first law is this sort of qualitative way of just trying to ask, what should stuff do? And what he came up with is that an object will maintain its state of motion unless acted on by a non-zero net force. Or saying that in simpler terms, an object in motion will tend to stay in motion, an object at rest will tend to stay at rest. Right? So when he's talking about changes in motion, he's talking about changes in velocities. And the reason why objects are going to resist any changes to that velocity or that state of motion is that they have this idea, this quantity of inertia. So this first law is sometimes called the law of inertia, and that inertia is that resistance to changes in motion. And we can see that captured with the object's mass when we look in equations, as we'll see shortly. But this more, again, qualitative law was that first law, just the first look, what should stuff do? But then Newton said, well, if there is this net force on our objects, what kind of change in motion will they acquire? Right? And this is where the second law comes in, and we see this very famous equation, F net is ma. So let's look back on acceleration. Can anyone remind me, what is our definition of acceleration? Like going back to basic definitions, right? Acceleration is what divided by what? Or conceptually, what does it measure for us? And if it helps, we can think that like an average velocity is a displacement per time, right? So an acceleration is a what per what? Change in velocity over time. Okay, perfect. Yeah, exactly. So when we're talking about a net force giving rise to a change in motion or change in velocity, well, that's captured in the acceleration, right? So this is a nice compact equation that gives you this cause and effect relationship, which is great. Um, and it also picks out a number of things for us. For instance, this quantity of force is a vector, and that makes sense because a force, simply put, is any push or pull. And you can push or pull in different directions, right? So it's a vector. And as a vector, it points in the same direction as the acceleration, since m is a positive quantity. The units of force should look like mass onto acceleration, so kilogram meter per second squared. And we're going to call that capital N for newtons for short. And we can see a proportional relationship here, assuming a constant mass, right? Double the force, you would double the acceleration given to the object. But then Newton had the question, well, if an object does feel this force, it's coming from some other object, some other thing. And he said, what about that guy, right? What about that other object in this interaction? What would happen to it? And this is where we have Newton's third law, where he claimed that for every action, there's an equal and opposite reaction. So if there's a force from object one onto object two, we should anticipate a force from object two back on object one that's equal in magnitude, but opposite in direction. And notice that forces that fit this Newton's third law form are often called action-reaction pairs. So if you see that phrasing, this is what it's referring to, one of these Newton's third law type of forces. And so when it comes to working these Newton's laws problems, anytime you see forces being referenced, we should be thinking about Newton's laws. And the way to set up the problem is to follow the thought process outlined here. So the first thing you want to do is draw a free body diagram or a force diagram. And remember, like I mentioned briefly last time, when we're drawing these free body diagrams, just draw the real physical forces on the object. Don't include components. Sometimes questions are pretty good about literally telling you don't draw the components, but whether they do or they don't draw the components, right? Just the real physical forces. From there, identify an appropriate coordinate system, right? Like, is it the usual sort of X, Y like we've been using, or do you need to tilt it like there's an incline or something else? Then write out Newton's second law. And like we noticed, that's a vector relationship. And as we talked about with projectile motion, when you get vectors in multiple directions, you can start thinking about components. So we can do F net as ma for the X direction, F net as ma for the Y direction, and that's very handy because that gives you multiple equations to handle multiple unknowns. And then, of course, once you've got things set up, dive into the math, solve whatever you've been asked to solve for. So we want to spend a little bit of time working through an example on that, but first we should bring up some common kinds of forces to see it on AP Physics 1. So you folks tell me, what what force does the Earth exert on objects? Right? If an object has a mass and it's near the Earth, what force will that object feel that's trying to pull it into the center of the Earth? Great question. Will there be space to draw components on a force diagram if you need to? Yes, yes, there will be. And one of the things we brought up last time was use only the space you need, because you should anticipate having more than enough space, right? Um, so needless to say, yeah, you'll have the room to do that. And that's something we'll talk about when we get to our example as well. It would actually be nice to have components, right, to visually guide you through the problem on your free body diagram. So the advice there is draw like a second one for that next part of the problem, but don't change the first part where they ask you for the free body diagram. Yeah, and the answer to this question is gravity, right? The force that objects near the Earth feel. So let's put that down. So the force of gravity is a force that any mass feels when it's near the Earth. And that force of gravity is sometimes called the weight. So to label that, you could use F for force, subscript W for weight. You could just call it big W for the weight force. Or you could do it like I do it and say F for force, subscript little g for a little gravity. The way you calculate this is you take the mass of the object and multiply by little g. And that's, again, that 10 meters per second squared magnitude of the acceleration due to gravity near the Earth. And so yes, so all masses like us right now feel this gravity force pulling us down to the center of the Earth. But presumably, no one here is actually heading to the center of the Earth. I'm sitting in my chair and I'm staying here. Some of you are probably having the same experience. Um, so there must be a force somehow countering this weight, preventing that from happening. Does anyone know the name of that force that's countering gravity as we sit in our chairs, that keeps us from moving through the center of the Earth and crushing our chairs? So gravity is the force that's trying to pull us down to the center of the Earth. I want to know what force is countering that. Ah, normal force. Okay, perfect, right? So that normal force is a force exerted by a surface to prevent the surface from being deformed. So when we sit in our chairs right now, gravity says, let's pull you through the chair, right? And the chair says, well, I'd rather not be crushed. So the chair exerts this normal force to prevent that from happening. And notice the choice of words. It's called the normal force because this force is always perpendicular to that surface. And those words, normal and perpendicular, mean the same thing. So this is one example of a contact force. Another example is friction. And we have that here. So our friction force is a resistive force that exists between surfaces in contact to try to stop or prevent any sliding from happening. So we see there's a few ways that friction can manifest. One is as static friction. So two surfaces could be in contact, but not sliding against each other. And this static friction is saying, good, let's keep it that way. So the way we can sort of conceptualize this is to think about an everyday scenario, like trying to move something. Like imagine trying to push some large, awkward thing like a fridge or something. I don't know. But you push on the fridge and it might not go anywhere. So first off, that suggests there is this resistive force. And secondly, it tells you this resistive force matched your applied force to prevent any motion from happening. So what you might do then is push a bit harder, and your fridge or whatever it is you're trying to push might still not move, suggesting that even though you've increased your applied force, the static friction force is able to increase and still match that Newton for Newton to prevent motion from happening. And what that tells you is that Static friction actually has a range of possible values depending on your problem, but it does max out. And that maximum resistance offered by static friction, we see here, it has a magnitude given by a coefficient of static friction, which just depends on the materials in contact, and then times that normal force. Once static friction has been overwhelmed, though, the kind of resistance immediately switches to kinetic friction, right? And the moment those two surfaces slide against each other, um, this resistive force is saying, hey, stop doing that. And this is our kinetic or sliding friction. And this has one value, just one fixed magnitude. And we see that here. The kinetic friction force is equal to the coefficient of kinetic friction. Again, it just depends on the materials in contact, times that normal force. So these coefficients, when I say they depend just on the materials in contact, I'm really suggesting, like, if you had wood on wood, that's one value. Steel on steel, that's another. Rubber on concrete, thinking about tires, that's another value, right? All right, so now that we've said something about some of those common forces, let's actually put it all together into an example. So looking at our question here, this is an example of a free response question at our end of chapter practice problems found in the AP Physics 1 prep book from the Princeton Review. And what the question asks is, well, it says this question concerns the motion of a crate being pulled across a horizontal floor by a rope. In the diagram below, the mass of the crate is m, the coefficient of kinetic friction between the crate and the floor is mu, and the tension in the rope is Ft. So there's another force, right? Tension force. This is a force found within a rope or a string that acts to prevent the rope or string from stretching or snapping. And it's worth noting that this is always acted along the length of the rope, and it acts away from the object the rope is attached to, which is to say ropes don't push, they pull. And it's constant throughout any given length of rope. But when you have this question that brings up forces like friction and tension, you should get the impression like, okay, I'm going to have to probably draw a free body diagram, set up Newton's second law, and work something out. And what the AP Physics 1 exam often does is it gets you to do that, but it breaks it up into steps in the free response section. And you'll see that if you take a look through some of the past exams that you can find on College Board's AP Physics website. But as one example of that, part A, draw and label all the forces acting on the crate. So they want the free body diagram. And again, don't include components here, right? Just the real physical forces. So thinking about those forces, what we can do is just draw our system as a dot. You don't have to recreate a perfect depiction of this crate or whatever it is, right? Just a dot is fine. And then label the forces that are acting on it. So let's think about those forces. You folks tell me, our object has mass, so what downward force will this mass feel? I need a downward force that a mass is going to feel, right? And that's coming from the earth on our mass. That would be our gravity force. And the object is in contact with a horizontal surface. So what vertical force from the surface does the mass feel? You folks tell me that too. Well, that downward pull, right, from the earth, that is a gravity force. But the upward push from the surface we're contacting, that's basically countering gravity or trying to act against that gravity force in some extent. What do we call that force? Right, it's that same force that our chair is exerting on us to prevent us from crushing the chair. Right, our normal force, perfect. And of course, we also have the other contact force here. They told us to worry about kinetic friction, so let's label that FFK for force of friction kinetic, and the tension force in the rope that we're told we have to worry about too. But that's it. Again, don't draw in components. If you want, off to the side, clearly distinct from the free body diagram, you can draw on your coordinate axes, but don't impose this on the diagram itself, because then it might look like this, and this are some other forces labeled as X and Y, so be careful there. But the labels you give the forces should be just, your standard labels. But again, if you put in W for the weight, that's fine. Big T for the tension, they'd accept that. And you can see examples of what they'd accept for labels on forces by looking through those past exams and the grading rubrics. But this is it, right? There's full credit for part A. For part B, it's asking us to compute the normal force acting on the crate in terms of a few of the labeled variables from the question. Well, first off, we're asked for a force. So if that's the case, think about setting up FNet as MA to work the problem. And because we had forces in different directions, we should be thinking about components. So let's, again, be clear. We're dealing with the XY direction. And we have force set up like this. We've got that weight. There's our friction force, the normal force, and the tension force, right? Like we had just drawn out. But this is me literally drawing a second free body diagram if I'm on the test. So I can actually put in the components of the tension, right? There's going to be some component acting in the horizontal, some component in the vertical. Here's the labeled angle theta. And you can draw in this second free body diagram if it helps for part B. Just don't mark up what you did for part A. Well, so these are the full forces, the actual full physical forces. All of the weight acts down, all of the friction heads to the left. So they're not components or pieces of those. But the tension force, the full force itself, acts up here. But the components or the parts or the pieces of that force that act in my coordinate directions would be this component here and this component here. Right. So this is tension in the X. And we don't want to put that on the free body diagram. And here's tension in the Y, and we don't want to put that on the free body diagram that they're evaluating. This second one that we draw out for part B, that's for our own help, right? And you can put that down. They have no problem with that. So you can let me know if that clarified your question. So setting up Newton's second law, we care about something in the vertical direction. So let's say F net in the vertical is equal to mass onto acceleration in the vertical, right? Think about those components. And in the y direction, we've got three forces. There's a normal force and this component of tension upward, and then there's the weight downward. So adding those together, the normal force and the tension component are up in the positive sense. We'd add in an amount of weight, but in the negative sense. And then if the motion here is all to the right, then it's all horizontal, in which case there is no vertical acceleration. So the right-hand side is 0. So now isolating for the normal force, we can bring that weight to the other side, and we can bring that component of tension to the other side as well. But notice here, we have normal force isolated. We have an expression for it, so that's pretty good. But they wanted it in terms of M, theta, G, and the total tension. We don't actually have that here, right? Because here our normal force is in terms of a component of tension. So this is good, but it's still only a partial result. So it would earn us partial credit. So we wouldn't, if we stopped here, it's not like we get 0. We'd probably get some credit for knowing to just start with Newton's second law and identify the right forces. But to get the full credit, we'd have to make sure we fully re-express normal force in terms of the quantities they've asked for. So you folks tell me, if I'm looking for this component that's opposite the labeled angle, do I want to take cosine of the angle or sine of the angle? Again, given that my component is opposite that labeled angle. It's a good time to point out too, like this is where SOHCAHTOA type trigonometry can be tested on AP Physics 1 when it comes to thinking about components of vectors like velocities or forces like we have here, or so on. All right, I need sine, exactly. That opposite pairs with sine. So this component in the vertical direction looks like the total force, but scaled down by sine of theta. And now when I make that switch, notice I now have normal force isolated and written out in terms of m, tension, theta, known constants like little g. And so we're good. There's nothing else we need to do. We can stop. So that's part B done. And then heading up to part C, they now ask us to compute the acceleration of the crate in terms of a series of labeled variables. Well, the acceleration should be in the horizontal direction since that's where the motion is. So we should look at F net as ma in the horizontal. Of course, we could, even if we weren't sure about that aspect, we could still think that we should look at F net as ma in the horizontal next, because the problem's asking about forces, we're drawing in the free body diagram, we're looking at Newton's second law. We've exhausted the vertical in part B, so all we're left with is a horizontal in part C. So it's another reason to think, let's set up F net as ma, but for the x components. So F net in the x is ma in the x. And if we look at the free body diagram we drew for part B, we'll see in our horizontal direction, the forces we've got are this horizontal component of tension and the kinetic friction force. So that component of tension is in the positive sense, the kinetic friction is in the negative sense, and this would be ma, and I can drop that subscript of x. Because like we noted, all of the accelerations in the x direction, so we don't really need that component. Like we don't have to put the subscript there. So now we can isolate for the acceleration by dividing through by the mass. So we get acceleration isolated, but just like we noted before, we're not done, right? Because the terms on the right don't match what they've asked me to present in the final answer. So let's re-express a few things. That component of tension, looking back at our diagram, this component is adjacent to that labeled angle, which means now we need to think about taking cosine of theta. So that component looks like the full tension, but onto cosine of theta. And recalling what we said earlier, kinetic friction can be re-expressed as a coefficient, which here they called mu, times the normal force. And then we're still not done because the normal force we have here isn't amongst this list of variables in the question. But what we can do is take our answer from part B, right? This expression that we had, and we can sub that in for our normal force. So the acceleration becomes ft cosine theta minus mu onto our normal force expression, which is mg minus ft sine of theta. And all of that is divided by mass. But notice now this expression we have for acceleration is in terms of the quantities they've asked for in the question. And so we're done. There's nothing else we're going to have to do here. So it's not exactly the prettiest of equations to be left with, but it is us having isolated for A, set it aside. It's in terms of the things they've asked for. We're done. There's nothing else we have to try to do with this to clean it up or make it look pretty, right? We're good. And so just as a note, if we had trouble getting part B done, that doesn't mean that we should just give up on the question, right? Because notice with C, we can still get full credit for C. Like if we knew to work with Newton's second law, that's probably a point for the question. If we identify the appropriate forces that are acted here, that's probably another point. And then we probably have a point awarded for the appropriate correct answer in the end. And if we had a wrong answer for B, or we didn't have one to supply for the normal force, like it wouldn't surprise me if they might still give credit for the question, right? Like if you put in an improper result, like maybe a plus sign here or something like that, because that was based on a previous problem, they wouldn't like double penalize you, right, for that mistake. So you did everything right here for C, so they'd give you the full credit. And you can see examples of that if you look through the grading schemes that are published with the past exams on College Board's AP Physics website. But that's our free response question for dynamics. And what that means is where we want to go next is to a little conversation on circular motion. So we'll turn our attention to circular motion. And like the label implies, we're dealing with movement in a circle. The uniform part is a little less self-explanatory, though. It means something is constant. So here that something is our object's speed. But just because an object's speed is constant doesn't mean that the velocity must also be constant. So can anyone tell me, when our object is going around in a circle, why isn't the velocity constant? What's changing for the velocity? What aspect of our velocity changes? And if we need a hint, you can let me know. I can see if I can give you any help, maybe point you in the right direction. A hint, yes. Well, a hint would point you in the right direction. It is accelerating when it turns, yeah, and that's kind of the question, like, how do we know that, right? So we'll know it's accelerating because we know the velocity changes, and we know the velocity changes because what aspect of our velocity changes? And remember, like, a velocity as a vector has two major parts to it, right? It's got a magnitude or a numerical amount, and it's got a direction as well. So when we move around in a circle, what part of our velocity is changing? So not the radius, we'll have a constant radius for the turn. But what's actually changing for the velocity is that direction. So remember, for an instantaneous velocity, the magnitude is the object's speed, which here we're claiming is constant, but the direction changes because it's always pointing tangent to the path or where the object's looking. So one moment we could have v1 like this, the next moment v2 would look like this. So the direction changes, so the velocity changes, and therefore there's an acceleration. So when you dig into the geometry, you can show that this acceleration is always center seeking. So we'll call it centripetal, and the magnitude is constant given by v squared over r. And if we think about Newton's second law, F net is ma. Like we said earlier, the net force points with the acceleration. So if the acceleration is centripetal, so is the net force. So F net we can rewrite as F centripetal, which becomes mass onto AC, which becomes m onto v squared over r. So that's where our equation here comes from. And where we often use that is, like I said, in tandem with gravity for a number of exercises. So it turns out that gravity force, m little g, that's an approximation, right? That's something we can claim for objects on Earth, but in a more universal or generalized sense, uh, gravity is an attractive force experienced between any two masses. And that force is given here by F big G is equal to big G, a constant, times the product of the masses interacting over their separation squared. And what we're showing here in the diagram is the separation goes from one center to the other. And notice how we set up an action-reaction pair here. But let's take a look at an example that pairs circular motion with gravity, and maybe we'll finish with that idea. That's not that example. Let's do this one. So for example 10, it says the moon orbits Earth in a nearly circular path at nearly constant speed. So there are some clues to suggest, hey, here we've got uniform circular motion, which should make us think about centripetal force and F net as ma. It says if big M is the mass of the Earth and little m is the mass of the moon, and r is the moon's radius, find an expression for the moon's orbital speed. Well, doing a quick sketch of the problem, we might say here's the Earth, here's the moon. It's in a circular orbit to some artistic integrity. And there's going to be this gravitational attraction on the moon pulling it to the Earth. And that is the one force the moon feels, and hence that one force would be the centripetal force. So let's note, in circular motion, we say Fc is mac. That Fc is like a net force, which is coming from just that gravity force. AC, like we noted before, that's v squared over r. The gravity force, we noted, is gmm over r squared. And we want to find that orbital speed v. So let's simplify the math. And notice here, the mass of the moon, it's the same on both sides, so it drops out. And the radius, if we multiply both sides by r, we could simplify that a little bit. So again, if we were computing a number, we wouldn't want to just shove in the numbers now, because maybe we didn't have the mass of the moon and we'd be stuck, right? But it turns out we don't need it. Or even if we had it along with these r values, you can imagine they're probably pretty big numbers, these masses and distances. So the math might get a little awkward. So it's nice to simplify it first. But now isolating for v requires taking a square root on both sides. And that leaves us with this expression here. And we're done. So notice here, just like with our free response question, if we're asked to compute a quantity, we need to show work. So we can't just say, oh, well, I knew this was a final result from a previous practice problem I did and just quote it. You have to show the work. Same thing with the free response question from before. You couldn't say, well, conceptually, maybe I know this is the expression for the normal force, right? And just jot that down. You have to show the technical details, the Newton's second law, to get the full credit for the question when it says compute. But that takes us up to about our time right now. So I'll cap the discussion here. Like I said, we have another content review session coming up. That's on April 22nd, same time, 6 p.m. Eastern. And there we'll cover the remaining topics from energy, momentum, simple harmonic motion, torque, and rotational motion. So thanks everyone for taking the time out of your day to be with us here today. I greatly appreciate it. And thanks for all the participation. That's also greatly appreciated. And again, tell all your friends, have them come by and check out that third review session. Thanks all.